Well, so so nothing to do with the Virginia or
No, it has to do with rainbow. That's all. Nothing else.
그쪽 화면에 왜 그렇게 나오지? 왜 그러나?
지금 손실 잠깐.
이 화면하고 다르게 나오는 것 같은데?
맞습니다.
아까는 왜 그랬을까요? 그지?
아마 그 뭐였지? 막 20분간 해가지고 화면 보기 잠깐 넘어갔다 돌아오고.
Alright, thanks for coming. So today we're pleased to have Neal Bushaw from Virginia Commonwealth University. Yeah, he's visiting, I guess, for 1 month during his sabbatical. Please.
Great. So thank you very much for having me here. It's been a pleasure to be here this week. And I am going to be here the next 3 weeks, and I want to do math with people. So this talk is much more about problems than it is about solutions. So I'll show you lots of interesting things, most of which I have a guess at the answer to, but no proofs. I'll show some proofs in the middle. But again, the point here really is just to show you what these problems are like and to try and convince you that they're interesting. I also handwrite all my slides, so if there are things you can't read, you have to let me know. I also get very nervous if it's quiet. So if you have questions, if you have things to say, just say it, just shout it out. You can even point out that there's an error on the very first slide. This is not what today's date is. So, this is joint work with a number of people, primarily with Puck Rombach and Dan Johnston at Vermont and Trinity College. That's the Trinity College in Connecticut in the US. As well as my former graduate student Vic Bednar, who's been at VCU for a number of years, was at the University of Richmond last year, and is now starting at Furman, I think this week. And I'll just start with what the big question is. So I want to know how many edges there are in a graph with the following properties. It shouldn't have a copy of some fixed graph h. So that graph that I don't like in this talk will alternate back and forth. Sometimes it will be called f, sometimes it will be called h. I used to call it h because it's a graph that I hate. But then I decided that that's a little bit mean, so I started calling it f for a graph that's forbidden, just to be a little bit more kind. But either one throughout the talk, h and f should always be the thing that we don't want to show up. And in order to quantify things, I need to know how many vertices are in the graph. Every graph is finite. Every graph in the universe has n vertices. And then if I'm going to count edges relative to not containing some graph h or f, it had better be a simple graph. I don't want to be able to get a billion edges in my graph just by putting in a billion loops or a bunch of parallel edges or anything like that.
So when you say h-free, you mean induced subgraph?
I mean regular subgraph. Yeah.
Subgraph.
So just purely subgraph. Yeah, so in this entire talk, there is no induced subgraph. There is no minor. Everything is just a pure normal subgraph. So you can't have a copy of h, even with extra edges tossed on top of it. And very soon I'll want this thing to be maximally h-free. I haven't motivated to you why that is yet, but it's sort of that if I have an h-free graph and I'm trying to count edges in h-free graphs, I don't want to be able to just say, well, you just take every subgraph of that. You just start throwing out edges, and you still have an h-free graph, and you get any number of edges that you want. So I'm going to focus on the ones that are as large as possible relative to being h-free. And so that's this definition. I'm going to say that you need to be h-free, but anytime you add an edge, you contain a copy of h. Again, that's as a normal subgraph, not induced. And I'll call these graphs H-saturated, or F-saturated. Okay, so again, it's two things at once, right? No copy of H, but saturated, so as soon as you add more stuff, you find one. Okay, so here's a silly example. That's a hexagon. It has no triangles. It's not saturated, because you can add the long diagonals without creating triangles. If you add in all of those, you get this graph, and that, it turns out, is maximally triangle-free. When I add edges to that, I find triangles every time. Okay, so again, I'm adding edges, not adding vertices, and I don't want to find a copy of H. Okay, so the one on the right is maximally triangle-free. It has 6 vertices. The one on the left has 6 edges. The one on the right has 9 edges. But the one on the left isn't going to count because it's not maximal. Okay, so I can just keep track. What numbers of edges are possible among these maximal H-free graphs? And I mark down 9 as being possible, but I'm not going to mark 6 since it wasn't maximal. On the other hand, this graph, the star graph, that is again triangle-free. If you add an edge to it, you do find a triangle. So 5 edges is possible. If you're already tired of my talk, you can try and figure out what happens for 6, 7, and 8 during the rest of the talk. Okay, so it turns out, no proof, but this 9 is the most edges you can have in a 6-vertex graph with no triangle. And 5 is the fewest number of edges that you can have in a maximally triangle-free graph on 6 vertices. And those are very special to me, so I'm going to call those the saturation number of the triangle and the extremal number of the triangle. Extremal number is the big one, the saturation number is the small one. Okay, and that's what's defined here. So I take the extremal number, it needs 2 inputs, it takes the number of vertices that I'm focused on and the graph that I'm forbidding. And it says, great, I'm going to use this sort of distal style notation for the number of edges. It will only ever show up in these extremal functions, I think. Just means the number of edges in G, subject to having n vertices and being H saturated. Okay, the opposite end is exactly the same thing inside the curly braces, but it's a minimum instead. If you remove the word H saturated from here and replace it with H free, it changes nothing about the extremal number. It doesn't matter in the slightest. And in fact, that's the way that you'll see it if you look it up somewhere. But I like this version because you can see that these two things are really just the top end and bottom end of the same set. Okay, so the extremal number has a very long and detailed history that probably most of you know, starting with maybe Montel's theorem, or maybe with some Zarinkevich stuff earlier than that, going on through Turan's theorem and the Edder-Stone theorem, Edder-Stone-Simonovitz, depending on your style and what you think are the important parts of that theorem. My advisor has strong opinions, so I always write it in a way where everything is listed. And the saturation number also has a long and detailed history that is maybe not quite as well known. Starts with really Zhikov, but only in Russian. So the traditional starting point is this theorem of Erdős, and Moon, which I'll mention a little bit later. And there's a couple of beautiful surveys by Ron Gould and assorted other people on these saturation numbers. Very well studied, but much less understood than the extremal numbers, I think. Okay, so extremal numbers are really nice, I think. And in particular, they obey some properties that make them relatively easy to deal with. One is that if you increase the number of edges in your host graphs, increase the number of vertices in your host graph from n to n plus 1, you still have a graph with no copy of f inside it. And so that means that the extremal number can only go up as you add vertices. It's also true that if you have some graph f1 living inside f2, then the extremal number for the smaller graph is at most as big as the extremal number for the big graph. So certainly if you have no copy of f1, you'll also not have a copy of f2. And that gives you some really nice tools for being able to compute with these things and figure things out. These will also be true for something that I haven't yet defined, which is the rainbow extremal number. Don't worry about it, but it will continue to be true. That will also be nice. On the other hand, these things are not true for saturation numbers, for either of the kinds of saturation numbers that I'll talk about. In fact, in the very last few slides of this talk, I'll introduce like infinitely many different versions of the extremal number and the saturation number, and this won't be true for any of them. And I'll show you a quick example. So, Erdős-Heinl-Moon gives you the saturation number for complete graphs. And this ends up being the saturated graph with no K4 in it. If you add an edge, it's got a clique of size 2 and an independent set joined together. It's a split graph. If you add in any edge, it has to go in on the right-hand side, and then you complete a copy of K4. So it's K4 saturated, and it has 2n minus 2 edges. Turns out that's the smallest number of edges in any K4 saturated graph. On the other hand, if I take K4 with a pendant hanging off of it, then this graph, made up of a whole bunch of copies of K4, is suddenly saturated. If I add an edge to it, I'll find a K4 with a pendant, but it doesn't have one in it already. Okay, but, oh no. How many edges are in that graph? Well, it's only 3n over 2, roughly. Smaller than the 2n minus 2. So even though you're forbidding a larger graph, the saturation number sort of went in the wrong direction. And this sort of non-monotone stuff happens all the time in saturation world. It's one of the very hard things to deal with. Similarly, for that other the top one, you can't just take a saturated graph on n vertices and add a vertex to it and hope that it will still be saturated. Because now you have to consider what happens when I add in all these extra edges incident to the new vertex. So you don't get monotonicity in either the number of vertices or in the forbidden graph. Okay. So here's a very general question that is the same as the question on the first slide. Now we've got some language for it. I want to know which edge numbers between 0 and the number of edges in the complete graph are possible in an F-saturated graph of size n. Okay, so we just saw the swap from H to F. And so that's what I define this thing called the saturation spectrum. Again, depends on the number of vertices and the forbidden graph, and it records the numbers of edges that are possible in F-saturated graphs. So, for example, Erdős-Heinl-Moon, which I've mentioned, tells you the smallest number of edges in a KP saturated graph. It ends up being this amount. It's exactly the same picture you just saw for K4. You take a clique on P minus 2 vertices and join it to an independent set. Adding in any edge has to go inside the independent set and gives you a KP. At the top end, you get whatever this number is from Turan's theorem. Maybe I don't want to bother writing it down. And so we know that both of those things are sort of the bookends of this saturation spectrum. There's the two constructions. Okay, great. So there's something about rainbows or edges or something going on. So here's where it gets a little bit complicated, and I'll take my time. There's a couple of layers of colorings and things. So again, I want to have an n vertex host graph that I'm going to call G, and a small forbidden subgraph, which unfortunately has switched back again to being called H. I warned you about this. H and F you can think of as being the same. And what I want to do is I want to try and properly color G in a way that avoids any rainbow copy of H. So what does rainbow mean? That's a philosophical question, but to me it just means that there's no repeated color. If you look at a rainbow, all the colors are different. There are colors in the world that you don't see in a rainbow. You don't see ultraviolet or infrared. I don't care. I don't care. I don't need to see every color in the world. I just need that there are no repeated colors. So that's what rainbow means to me. So on the left, you see a K4, which is properly colored, but not rainbow. In fact, it's like as un-rainbow as possible. Every edge has its color repeated somewhere else. And the one on the right is rainbow. Every edge is colored differently. Okay. So now we have to deal with that maximality stuff that was easy for the regular saturation. I just said, well, it's just maximal, and then I moved on. But now maximal relative to what? Because now we've got these colorings moving around, and I want this maximality to be a property of the graph itself, not a property of the coloring of the graph. Okay, so I'm going to call a graph rainbow H saturated if it has a proper edge coloring, which is rainbow H free. But when you add an edge and try to color it, every proper edge coloring of G+y contains your forbidden subgraph. Okay, so the graph itself can be colored avoiding H, but when you add an edge, you can no longer avoid H, no matter how you color it. And to avoid writing the word rainbow about 11,000 times in the next 40 minutes, I'm going to call these H star saturated. I have a version of these slides where all the stars are little tiny rainbows that I painfully drew in, but it turns out that that's basically impossible to read. Okay, so let's see an example. There's a problem with paths that I've been dealing with my whole life. My very first paper was about forests of paths. And the first thing that happens when you talk about a path, P4, for example, is someone says, is that length 4 or is that 4 vertices? So it depends on which. If you look in sort of what I consider the big 4 math books, the graph theory books, 2 of them say it's the number of vertices, 2 of them say it's the number of edges. And so I'm going to write it in a way that everyone hates equally, which is I'm going to call it P3.5. Right? There can be no doubt what that has to mean. It has to be the one of length 3 on 4 vertices. Okay, so here's a graph that is P3.5 saturated, rainbow saturated. You can color it this way. That has no P3.5 that is rainbow. In fact, it doesn't have one at all. But if you add in an edge to it, no matter how you color it, the 4 edges around the central vertex have to all be colored differently. And so you can always find your P3.5 that is rainbow. You can avoid the color you used on the new edge on one of these paths. So that's a P3.5 star saturated graph.
I have a question. So
Yes.
when you say graph has a proper edge coloring, which is rainbow H free, actually you can just color every edge with different colors, right?
So that always gives you a rainbow copy, right? I want it to not have a rainbow copy of H. I want to forbid rainbow copies. Yeah, so you're absolutely right.
Oh,
You
I
can
see.
always color every edge differently and get yourself a rainbow copy. So here I'm doing the opposite thing.
Right, okay.
And that's also the reason that I force these to be proper colorings, not like Ramsey-style arbitrary colorings, because you could color everything the same color and you won't get any rainbow copies.
Mhm.
I should point out that there are at least 2 competing versions of what rainbow means in the literature, including at least one other version of what rainbow saturation means. And I think none of us knew it when we wrote our papers, so they all just call it rainbow saturation. But in the papers that you'll see in the next years, this will be called proper rainbow saturation, just to keep these things separate. And the other versions of rainbow that I know of, usually you have a graph and you color it in a way that has no rainbow H, and then you add new edges in colors to that coloring. Here the colorings on the graph with an edge added don't have to have anything to do with the original coloring. Okay, so they're very different problems. As far as I know, there's no translation between the two kinds of results. Okay, here's a different graph, which is P 3.5 star saturated, and it's saturated for a very different reason. So once again, you can color it in a way where you don't find a P 3.5. So it's certainly rainbow P 3.5 free, but here there's no edges you can add. So by default, it's saturated. Okay, somehow less interesting, but we gotta consider that. So I wanted to show you a picture. Questions on what rainbow saturated means?
So when you mean by the, so when you mean that there's no, there, so what there is, when, so you mean by that there always exists a rainbow H, that means that there could be like in different proper colorings, then there could be some different copies of rainbow H.
Definitely. Yep. It may be in a different place always. So if I say that this graph is rainbow H saturated, what that means is first I can color it and not see a rainbow H. But then when I pick an edge and add it, and then try and color it in any way, somewhere, I don't know where, I don't care where, somewhere I find a rainbow copy of H. You can convince yourself that this will have to be involved somehow, but it's a little complicated, right? Because this changes both the kinds of colorings which exist, and it also changes the subgraphs which exist.
Oh, so the rainbow copy doesn't necessarily have to use
Doesn't necessarily use the new edge. Which means more or less that no tool from old saturation, from the other kind of saturation really applies directly. Okay. Questions while we're stopped? Okay, great. Thank you for breaking the ice. Okay, so then I can define the rainbow saturation number in exactly the same way that I defined the regular saturation number, since I overloaded the word saturation to mean what it needs to mean. So again, it's just the minimum number of edges in a saturated graph. In this case, in a rainbow saturated graph. And lucky us, we can define the rainbow extremal number in exactly the same way as the largest number of edges in a graph on n vertices, which is again rainbow H saturated. The origin of this comes from the extremal end. There's this beautiful paper of Peter Kivash and Dhruv Mumbai and Benny Sudakov and Jacques Verstrada, where they prove lots of important things about the rainbow Turan function. They call it the Turan function. My advisor won't allow it, so I call it the extremal function. And this is a beautiful paper. You should go read this paper. You should read it this weekend. It's a great paper. And in particular, they proved this theorem. It's proposition 1.1. You can tell it's important. It says that the rainbow extremal number satisfies, first, a nice monotonicity thing relative to the normal extremal number. So the rainbow extremal number is always at least as big as the normal extremal number. Why is that? Well, if I take a graph which doesn't have a copy of H, and I color it however I want, and it certainly won't have a rainbow copy of H. One is not going to magically appear. So the rainbow extremal number is bigger than the extremal number, or at least as large. But importantly, it's also bounded above by the extremal number plus something that goes to, that is little o of n squared. So it's sandwiched. If you know the Erdős-Stone theorem, that tells you for graphs of chromatic number at least 3, this is pretty much determined. The regular extremal number is known up to a term that's little o of n squared, and so the rainbow extremal number is 2. And even more than that, they proved that if you have a graph which is color critical, then for large enough n, small things may happen when you have very small n, but for large n, they're exactly the same as one another. If you do go read this paper this weekend, read their definition of color critical twice, because it's not the definition of color critical that you might know if you know a definition of color critical. I'm not going to define it here because I'm never going to mention this again. Okay, so there's the monotonicity and then the little events grid. So one thing happens here. That means, like I just said, that sort of the remaining interesting graphs for determining the rainbow extremal numbers are the bipartite ones. Felix Clemens, who's here, has worked on that for even cycles. I'm very interested in it for trees. And the list of trees for which the rainbow extremal number is known is very short. It's P 1.5, 2.5, 3.5, balanced double stars, and stars. That's all. Everything else is open. Yeah, I'll maybe mention some more about that later, but I, to be perfectly honest, can't remember. Okay. So our guess is that the same thing happens for the saturation number. The rainbow saturation number should be at least as big as the normal saturation number. But to be frank, my intuition bounces back and forth on this. I've conjectured both that this is true and not true at different times. Currently, I think this is probably true. We have no example, of course, where it's the other way around. You can talk yourself in circles, say, okay, so if I'm allowed to color it, that should make it harder, but it also gives me more flexibility on what the graph can be, and you can do this in the mirror yourself for hours. This I would love to prove, and it seems like it, and we thought when we first started working on this that we must be morons, because surely this is easy, and it doesn't seem to be at all.
Do you know any class of graphs H where this conjecture is true? Like simple?
Only silly ones. I mean, it's true for triangles and stars, where every coloring is rainbow.
Oh.
So that the two must be the same.
Okay.
But I think those are the only ones where I know it.
Huh.
There must be some, but I haven't found them. I'll show you some in a bit where they're separated from one another. Okay, so as an example, here's a nice result of Casanituza. I'll show you sort of their better known result in a moment, but they proved the saturation number for P3.5. They showed that it's basically n over 2, except there's some parity things that you have to deal with. And you can just take a matching and then a triangle. That graph is always saturated relative to P3.5. Oh, that we already talked about. Is P3 that or that? Okay. So, with Puck and Dan, we proved that for the rainbow saturation number, you get something strictly larger. The rainbow saturation number for that same path is a little bit bigger. It's 4/5. Again, up to some divisibility stuff. And there you can take copies of K14, the same graph that we saw a couple of slides ago, or K4, again, which we saw a couple of slides ago. If you add edges between them and color it, you can convince yourself, or you can read in the paper, that you'll always find a copy of P3.5 with all of its edges colored differently. Okay, so again, the point here is these are two graphs where the saturation number and the rainbow saturation number are asymptotically different from each other. They're not just different by a constant. One is much larger than the other, in the direction that I told you they should be larger. Okay, but there are even some cases where you can sort of prove some easy bounds on the rainbow saturation numbers, and it doesn't quite deal with anything. So Ullman in 72 proved the saturation number for a 4-cycle. I just wanted to give a non-tree example. It's 3n minus 5 over 2. I'm not going to show you what goes on there. There are many more parity issues and cases to go on. I can't just show you an easy construction. Puck and Dan and I proved initially that the rainbow saturation number is somewhere between n and 2n minus 2, which is fine, but unsatisfying. Because that doesn't tell you that it's not 3n minus 5 over 2. You don't learn that it's different. We hoped maybe it would be smaller and we would deal with our conjecture. That ends up not being the case. You can see the upper bound comes from a wheel. You can color a wheel in this very particular way where the spoke colors line up to the rim colors that are 2 edges away. And that means that when you find a C4, it'll always have 2 edges that match. No matter where you find your C4, you get 2 edges that match, which in particular means it's not rainbow. And lucky us, this year, Anna Huffpop, Bernard Ludichki, and Thomas Majerick solved the rest of this, and they proved that, in fact, the saturation number for C4 is 11/6 n, more or less. Again, there are divisibility things going on in the first bound, and some large number of things going on in the second bound. Okay, but importantly, 11/6 is not 3/2. It's close, but it's not 3/2. So again, we get a tree and a non-tree where these two things are separated from each other asymptotically. Okay, so let's stop talking about particular examples and see what we can do in general. So Cassini and Tusa famously proved that for any h, there's a constant so that the saturation number is at most C times n. That is unlike the Erdős-Stone theorem that tells you that for graphs of chromatic number 3, you get dense h-free graphs. Here, they're always linear size, at most. And in fact, they proved something stronger, which I'm going to need in a slide or two, although it's not usually stated this way, which is you can take a whole family of graphs and forbid all of them, and ask yourself to be saturated relative to that family, and the saturation number is still linear. Okay, that's going to give us a really unsatisfying way to prove that the rainbow saturation numbers are linear. So I'll first show you a very unsatisfying proof, and then I'll show you a more satisfying proof that doesn't prove all of the cases after that. Okay, so here's the unsatisfying proof. You take a forbidden graph F. I let H contain all of the order n graphs which have a proper F-free, rainbow F-free coloring. That's a monotone property. Monotone properties can be characterized by a finite set of forbidden subgraphs. So it has a forbidden subgraph description. And so if I take a graph which is saturated relative to that entire set of graphs which have proper F-star free colorings, I will get a graph which is rainbow saturated. And lucky us, the Cassini-Tusa theorem lets us find the saturation number for whole families like this all at once and get a linear bound. So you get a linear bound in, again, what I think is a very unsatisfying way, because not only does Cassini-Tusa not tell you what this constant is for your family of graphs H, you don't know what your family of graphs H is, because it's just the ones that can be rainbow free colored.
Is this F1, F2, blah blah blah? Is it can be infinite?
It will always be finite, but in fact Cassini-Tusa applies to infinite sets as well, so it doesn't really matter. It's easier to prove that every monotone property has a forbidden subgraph characterization if you don't care that it's finite. Of course, here I'm specifying n vertex graphs, so everything will be fine. Okay.
Show the statement again. The previous.
Oh, I don't think I actually stated anything.
Yeah.
So the statement is that the rainbow saturation number is at most some constant times n. Is always linear.
Uh-huh.
And again, it comes from the regular saturation numbers being linear and doing this trick to get the rainbow saturation ones from the regular saturated ones.
You should know that the limit of C exists. So what I mean is the saturation number over n and tending n as an infinite, then that value has a limit. I mean
So it's a constant, and then n varies, right? So it will get larger and larger and larger.
so what I mean is for every fixed graph f, the saturation number can be written as C times n plus beta over n. For
Yes.
some course.
Yep. Yeah.
Okay.
Exactly. Yeah. So if you pick a graph, there exists a constant, so that the saturation number is at most C times n. Okay. So this is a weak version of that theorem. It says that it's not true for every graph, but I'm going to specify that it must be even cycle free. So this was the first thing that we proved in the first paper about rainbow saturation. It says for any even cycle free graph, there's a constant so that the saturation number is at most that constant times n. And I'll show you this proof as well. Again, even though it's strictly weaker than the last theorem. But I want to show it to you because you can actually get some idea for what the constant is. You can actually extract something from it. And you can see where this thing comes from. It's not just a Cassini-Tusa black box. Okay, so it's very similar to the original Cassini-Tusa proof, if you know that. But again, there's no colorings in that theorem, so we need to inject colorings somewhere. And so the way that it works, this is going to be a very sketchy overview. It's going to fit on this slide. I'm going to carry out no details. The thing that we're going to do is we're going to define a sequence of families of graphs in the following way. I'm going to let F0 be the original forbidden graph. And then I'm going to, every time I have a family F, I'm going to define Fi plus 1 by looking at the graphs in Fi and removing a maximum size independent set from them. Cassini-Tusa, they just remove a single vertex every time and they take these collections of graphs. Here I'm removing maximum size independent sets. And there's a slightly strange thing here, which is I have lots of graphs in Fi, and I need it to be a maximum size independent set, not just in the original graph, not just in the graph that it came from, but maximum size among all of the graphs in the previous family. So it may be that you can't remove a maximum size independent set from many of them, in which case they'll fall out. They'll disappear. Okay, so there's the same thing written symbolically. Don't read it. And I'm going to stop if at some point I see a graph which is a bipartite graph. And I'll set k equals I. I say bipartite, really even cycle free is what I mean. So if you do this, if you started with a even cycle free graph and you remove things from them until you get a bipartite graph, you end up at a bipartite and even cycle free graph. Okay? And there's a theorem which is implicit in the work of Corey Palmer and some others, again, Dan Johnston and Puck Rumbach, which gives you a constant for the rainbow saturation number for forests. Okay. In fact, they prove an upper bound on the extremal number for forests, but the rainbow extremal number is at least as big as the rainbow saturation number. Okay. We don't know what the rainbow saturation numbers are for forests in general. I have a paper on that as well. I'm very interested in it. And I told you already the only ones we know are like very silly short paths and double stars or something. You can get explicit constants for some trees in a paper of mine with my graduate student. But the point is that once you get that last one, you can put down a graph which is saturated and which has very few edges. So you take a graph which is saturated relative to that last bipartite graph that you got on some number of vertices. You don't know how many since you've been removing maximum size independent sets this whole time. But you know that it has linearly many edges in its order. And then you build this thing back up. There's a way to start with that last graph that you got, GK, and build up graphs as you go, which will still be saturated relative to the intermediate families that we worked our way down. So we have this last one that was saturated relative to FK. Then you'll get one that's saturated relative to FK minus 1. And it sort of, once you get to one where you can put down a rainbow saturated graph, then poof, everything else works out. Okay, so this is the part that I'm not telling you any detail about, is how to do that. The point is that you can do that in a way where there are very few vertices which have changed between these saturated graphs. That is, they don't go up by huge numbers of vertices in any one step. GK will remain rainbow FK saturated as you do it. And that means that when you get down to the end, you've got a graph which is rainbow at H saturated, and you can count how many edges it must have by how many edges you took out in this process. So again, if you know Cassini-Tusa, the only difference here is that instead of removing a single vertex every time and looking for stars at the end, we're removing maximum independent sets, that is whole color classes, maybe at once, the biggest a whole color class could be at once, until we see something where we know the rainbow saturation number. Yes?
Can we make this as an algorithm to find the actual constant C prime?
Yes.
If we have the algorithm for maximum independent set.
Yes. Yep. Yeah, so for any particular small graph that you wish, we could work through this in, I don't know, 20 minutes. Okay, maybe an hour. Depends on how small your small graph is. But yes, you can reverse engineer it. Okay, so the most obvious thing to do is to try and remove the even cycle free condition. That will require us to know something more about some rainbow saturation numbers for very sparse graphs. But anything that you can do that includes some graphs with even cycles in them will give you new graphs for which we can use this, as you say, algorithm to determine the constant. Okay, so you can decide if this is interesting or not. Again, we already knew that there's a short proof that they're linear, but this gives us a way of getting an idea of what the saturation numbers really might be, or at least bounds on them. And I'm going to move on from rainbow saturation for a minute, well, for maybe 7 minutes. Really, I think everything that I haven't shown you is open in rainbow saturation. And really everything else. There's this nice paper that I told you that found the constant for C4. They proved bounds on C5 and C6, and that's all. Okay. So now's the part where we go off the rails and I just start throwing open problems at you. So what if we make things that aren't quite rainbow? Or barely rainbow? So which one is which? Which is the one on the left? Is that barely rainbow or not quite rainbow?
Barely?
Why is it barely?
Because if you remove one edge, then it is rainbow.
Yes, so I think that makes it not quite rainbow. But I agree. These words don't mean anything. On the other hand, on the one on the right, it's like it only has one edge whose color doesn't appear anywhere else. So that one's barely rainbow. Right? The red edge is repeated, the black edges are repeated, and you have this blue one and the yellow one whose colors don't show up anywhere else. Okay. So I'm going to call a coloring K unique if at least K of its edges don't have their color repeated. So a graph is rainbow if it has M edges and it is M unique. Right? That says every edge should get its own unique color, and one unique says there's at least one edge whose color doesn't show up anywhere else. And so then I can call a coloring KF free if it has no K unique F in that color. Okay, so again, same thing we did with rainbow. First we define what it means to be F free. What's going to be next? We must define F saturated. And it's exactly what you think it should be. It's KF saturated if it can be colored in a KF free way. But when you add an edge, you can't do it anymore. If you thought saturation was non-monotone, this thing is out of control. Okay, once you have a definition for saturation, you can define extremal numbers in this way. It's exactly the same thing that we had before, except it has a K in front of F saturated. You can define the saturation number as the minimum over the same set. And in fact, that gives you this sort of chain of conjectured inequalities about these K unique things. Again, I alternate. Today, I'm sure that all of these are true. Tomorrow, who knows? Tomorrow's Saturday, I probably won't think about it. By Monday, it might be false again. And the important thing is that up at the top here, that's if you have saturation with the number of edges being K unique, that's the same thing as the rainbow saturation number. At the low end, in fact, this is the at least second typo. It's the second one we've caught. The regular saturation number is the same as the zero unique saturation number. Because that says, I don't care how many edges it has that are uniquely colored. You can do the same thing for the extremal numbers. Those ones are nicely ordered. If you have a graph with no K unique copy, it won't have a K+1 unique copy either. And again, they go from the extremal number to the rainbow extremal number with a third typo, although it's the same as the second typo, so maybe it doesn't count. It should be EX0, not EX1. And then you get, so that's infinitely many new parameters. Infinitely many new saturation functions and extremal functions. And for each one of them, you can ask which numbers of edges are possible between the saturation number and the extremal number. So for every one of these, you can ask the saturation spectrum question. And you get this whole chart where for almost every graph, I know nothing. I don't know a single one of these values. For almost every graph. For graphs of chromatic number 3 or higher, I know what this is, at least asymptotically. And for some graphs, I also know the saturation number. I showed you all the graphs where I know the rainbow saturation numbers. If you want a nice problem to work on, pick a small graph and point at this chart at random and try and fill it in. Okay. There are a few double stars where we have bounds on these K unique extremal numbers, but none where we know the whole spectrum. And you can go even further, because this whole time we've just been counting edges, and why should we just count edges, right? Edges are just a very special subgraph. So maybe I should do something like count the number of triangles in any of these and maximize not just the number of edges, maybe I want to maximize the number of triangles. Those are the generalized Turon numbers. You can do the same thing for saturation. Among all the saturated graphs, which ones have the most copies of H? So in this terminology, now we have H and F. The H is for how many, the F is for how bidden, for forbidden. How bidden, nice. Again, and you get this wild collection of things. There are a few graphs where this is known. There are a few combinations of graphs where this is known. Everything else is open for every graph. Truly every graph. And I think I'll stop here. So this is, I searched for a rainbow in Daejeon, and this is apparently the rainbow fountain. It didn't look especially rainbow in the pictures. If you watch the video, it actually is rainbow, I guess. All right, thank you.
Thank you.
Zero unit.
Any questions? Questions?
Are there any concepts or definitions which are the rainbow analog of the kind of bootstrap population or big saturation?
Yes. So there was a project at the GIWC, Graduate Research Workshop in Combinatorics, a couple of years ago that worked on rainbow weak saturation, which is really a coloring version of Bootstrap, as you said. But I think they couldn't even agree on what the definition should be.
I was in that group, so I can say
Yeah, I don't know.
I mean, we had a definition which I would kind of argue was the wrong definition, but it was a definition you could prove things about, whereas the thing that I would say was the right definition was like very hard to get any sort of grasp on.
Yeah, so this thing that we mentioned where when you add in an edge, it changes both what subgraphs you see and what the colorings are. When you deal with weak saturation, typically you want the new copy to use the new edge, and maybe that doesn't happen. Maybe it appears elsewhere in the graph. So there are a number of ways that you can define the rainbow weak saturation. Which was the other one you mentioned?
Bootstrap population.
Yeah, so bootstrap percolation and weak saturation are the same. You can also talk about semi-saturation problems. So what if I don't forbid a copy of F in the original graph? What if I just want the smallest number so that when I add an edge, I get more rainbow copies? This is the semi-saturation number, which I think is also entirely unstudied.
Is there any OEIS sequence that shows about the spectrum of the saturation?
So I have had some code running on the cluster at VCU for like 2.5 months. And if it ever outputs anything, I will certainly upload it to OEIS. I mean, because you need to iterate over all edge colorings of your host graphs, which are typically large, there's not a ton you can do computationally. Or at least not a ton that I can do computationally.
So which kinds of tools are used in your work or previous related results?
Yes, so mostly I stare at the ceiling. I try and come up with graphs where they have few rainbow copies, or where the rainbow copies are all going to be concentrated in one area of the host graph, and then try and erase edges from my whiteboard until they become truly saturated. There are no big techniques. It's very much the creative style you've got to come up with argument. I mean, it's very ad hoc for the particular graphs where we can get balance. Except in the case of Cass and Utuza, where the tool is do exactly what they did, but with bigger sets.
Is there any work on rainbow saturation problem for minors, not subgraphs?
I don't know the answer to that. I would not be surprised if someone was working on it, but I haven't seen anything. And well, yeah, I don't know. There may be a reason. I don't know anything about minors. I don't know. It's a good thing to think about.
I guess. Is there anything directed in that direction? So, like, if you ask, if you say that saturation is there is an orientation that avoids a given diagram.
Everything I know about digraphs I learned from your talk. So I don't think you mentioned anything. So I don't know.
I think it has to be a simple.
I would be happy to talk about it, but I have no idea. All of this is very new, right? The rainbow extremal numbers were defined in 2007. The rainbow saturation numbers were defined in 2020 on archive, 2022 in publication. So it's all very new.
So any other questions? So if not, let's thank the